Okay, well, thank you very much. It's a real pleasure to be here. I'm Michael Garwood. I'm a professor in the radiology department, but I'm kind of a physicist more by trade. I grew up in a small town in Michigan. Mom and Dad didn't have any money. I wasn't really sure whether I was going to go to college or not, but I was all about having fun, as you can see, at my young years. But I did have an older brother that did go to college on a scholarship. He ended up in California, and he said in the 1970s, if you're a resident of California, tuition's free. That's long gone. He said you can establish residency in your first year if you can get into a school out here. So I applied to one college, and I made up my mind, if I get in, I'll go, and if I don't get in, I'm not going to college. So I got in the University of California, and I went, and because I had an older brother that was a chemist, I decided I'd take some science courses, and boy, was I inspired by my professors. I love biology, I love chemistry, and I was all in. And so anyway, I ended up here, came here to postdoc with a guy who's the director of our center, the Center for Magnetic Resonance Research. That's been 32 years ago now, and I work there where we have MRI scanners, magnetic resonance imaging systems. You may have heard of it, maybe you've even had one. Most people these days have one time or another in their life. And it's a very strong magnet, and it allows you to see inside the body. And so these are just two slices of somebody's brain. Of course, they're alive, and these are the kind of pictures you can get in like 20 minutes going and lying inside this very large magnet. And what I do, and what I've been doing, and most people over at our center do, is try to make this thing better. And what I mean by better, make it faster, higher spatial resolution, being able to see different tissues better. For example, you can see here that there's contrast, and being able to see, like the cerebral cortex, the gray matter from the white matter. And trying to make it more available is another thing that we're doing. In fact, that's my major focus right now. It's a big physics and engineering project to try to make a small magnet that's just slightly larger than the brain. Because you may know, if you had an MRI scan, it's a big, expensive machine. You go inside this tube, and it can be claustrophobic, and it's noisy, and it's unpleasant. And they're only in major medical centers or big academic institutions. So I'm trying to reinvent the way it's done so it doesn't have to be done in this very large magnet that produces a very uniform magnetic field because it's so large. If you have a small magnet the size of the head, it's not going to be a uniform magnetic field. But what I want to do today is tell you about how magnetic resonance works, and I hope by the time you leave here, you're going to know exactly how it works. It's some really simple physics. But how does this thing that just produces a magnetic field, how is it allowing us to see inside the body? And what it takes advantage of is spin. And spin is one of the most incredible things. So many things are spinning, from this planet and the planets to nuclei. So right here I have a water molecule. It has oxygen, it has two hydrogens. And our bodies are mainly water, and that's what we're imaging when we look inside the brain. We're getting pictures of the water. Not only it's a picture where the intensity of the picture tells you about the concentration of the water, but it also tells you about what that water is doing. And a lot of what we do is develop ways to interrogate the water to tell us more about what it's doing so we can better diagnose diseases. But anyway, we take advantage of spin. And so when you have the hydrogen in the water molecule, and there's two of them, has a nucleus, and in that nucleus, each nucleus has a proton, which is a positively charged particle. And that proton is spinning. And as you heard from the talk about the TMS, when you have an electric field that spins, you can create a magnetic field, okay? Or a rotating, a charge through a coil loop creates a magnetic field perpendicular to it. If I have a charged particle that's spinning, I get a magnetic field that's perpendicular to it, okay? And that's what's happening at the proton. Each proton has a small magnetic field, but also know that it's spinning, so it also has angular momentum. So those are two important things. So now I'm going to go on with my demonstration to show you how it works. So I don't have a magnet here. I couldn't bring one of our magnets, it's just too big. So I have to use a force, and like instead of a magnetic field, I'm going to use a gravitational field. And I'm going to use this wheel here. And so if I hold this wheel up like this, and I let go of it, there's going to be a force on it. Oh, my mic's not working? Okay. Probably got to turn it on. That would help. Get it? There we go. I can operate an MRI machine, but I can't operate a microphone. That's something. So you know what's going to happen when I let go of this. And there's a force on it from gravity pulling it down. It's just going to go like that, right? But now what happens if I give this thing angular momentum? And remember, I just told you that the proton in the hydrogen nucleus has angular momentum and it has a magnetic field. So I'm going to give this wheel angular momentum. So now it has angular momentum. And an angular momentum is a vector. It has an amplitude and a direction. And so if I'm spinning like this, there's a vector along this direction due to angular momentum. Now I get this thing spinning, and what's going to happen when gravity pulls down on it? Is it going to do what it did before? Let's see. No, something remarkable happens. It doesn't fall over, but it's doing something else. It's rotating around, and that's called precession. Okay, you can do this at home. So something unique is happening here, that the force of gravity, which I have two vectors now, right? I have the angular momentum along the direction of my index finger and the force of gravity pulling it down, and I'm getting a rotation perpendicular to that. It's a cross product. If you've had that in school yet, maybe not. But so it causes this precession. And the nucleus, the proton in the hydrogen nucleus, is doing exactly the same thing when it feels the Earth's magnetic field. The magnetic field of the magnet. It also feels it with the Earth's magnetic field, but it's a very small effect because the Earth's magnetic field is very weak compared to the strengths of the magnetic fields that we're using in these magnets. So I want to just show you something else. So if I do this, if I change the angle, let's say here I'm at 90 degrees, it's going around at some frequency. Let me change the angle a little bit now. It's going around again. You can't really tell, but it is the same frequency. That rotation frequency is the same no matter what the angle is. But if I put it all the way down here, pointing with the gravitational field, it's there, but I can't detect it. Okay, so to see it, I have to do something. So this is what happens when you go and you lie in the magnet. You're not going to get any signal until you do something, because what's happening when you lie in the magnet, all those magnetic vectors, they go to be to a low energy state aligned with the magnetic field. So I have to apply another field just at the right frequency to make it come up. And that's the resonance condition. If you notice what I did, I put another torque on it at right angles, and I was moving at the same frequency as that rotation. So that's it. That's the principle of magnetic resonance. We get these signals. The signals come out just the opposite way that thing works. I have a coil here, and this magnetic field that's oscillating around induces a current in my coil. That's what I'm picking up. That's my electrical signal that I'm converted into magnetic images. So that's it. I'm happy to answer any questions. Really?
All right. So I have a question.
Oh, good.
So why would my magnet make my muscle twitch? or neuron depolarize, and when I go and lie in the MRI, because they're the same intensity, I'm not switching all over.
There is, so we do switch some magnetic fields in MRI to do spatial encoding. And there can be peripheral nerve stimulation, exactly like you showed, and so we don't switch that fast. We're careful.
So that's the thing between going 0 to 20,000 times the Earth's magnetic field versus it's relatively stable in the MRI. So we have the same strength typically, but the way we fluctuate the magnetic field is what my trick is to make my muscle twitch or my neuron twitch. It's the same principle.
Yeah.
I see people are getting, well, question, but we'll take the question, then we'll go to lunch.
Is that why an MRI takes a while because it has to go with the magnetic field?
Good question. No, MRI takes a while because the signal is very weak. I said that our protons are magnetic, but they're very weakly magnetic. In fact, actually, we only are able to make images is because we have so many protons. And if you put 1 million water molecules into an MRI magnet, say of like 1 Tesla, you only have like one more out of 1 million align with the magnetic field than is anti-parallel with the magnetic field. They're so weakly magnetic, but we only are able to get enough signal because we have so many, and we take some time, and that's called signal averaging to do the imaging. But things are getting better all the time. The electronics are getting better, and that's part of the things that we do, like the coils that are used to make the resonance condition. They're very critical, and so constantly technical improvements are happening. That's a lot of what our research is about that's making it faster. And I think someday an MRI will be, you'll be on a table and you'll just go right through the thing and it'll be done in a few seconds.
Well, it was a great question, and I'm glad we waited for that one.
Yep.
But with that, I think we'll go to lunch. So let's thank our speakers one more.